notations. And that's joint work with Chris Hall and Julia that's currently in progress. So I'm just going to allude to some of that. All right. So first, well, where are we taking roots? Anytime that you're talking about, like you're going to be looking to take a root, you have to think about, well, what field are you taking a root in? So our setting here is going to be Puzzo series. And throughout this talk, K is going to be an algebraically closed field of characteristic 0. So what's a Puzzo series over K? Well, it's a series that has this form, right? And actually, can you see my pointer right now or no?
Yes.
Yes, awesome, thanks. So these series, they look, they're sums of terms AI, t to the im, where these AIs, the coefficients, are coming from that fixed field K. And the index I is just an integer, for all integers above some lower bound L. And then there's some fixed denominator M, right? So just because that's a lot of notation, let me actually just give you an example of a Puzzo series. So here's one down here, right? So S. So I'm taking 3t to the negative 1/2 plus pi t to the 0 plus 2t to the 1/2. And then I'm going up sort of by exponents by 1/2. All right. So we call the set of those exponents that appear in a series the support of the series. So in this case, the exponents that appear are -1/2, 0, 1/2, 1, and then the ... is supposed to indicate that I'm going to keep going like that. 3/2, 2, etc. So I'm also going to denote the field of all such series, of all Puzzo series, with this K curly bracket T. All right. So I'll try and remind you the first few times so that shows up. So these things, are a well-studied field, but then later on, and we'll talk about the complexity of root, finding roots there. But then later on, we're going to talk about finding roots in a more general setting. So we're going to generalize the Puzzo series to a kind of series called a Hahn series, right? So in that case, again, you need a fixed coefficient field K, just as before. But in addition, now we need a group, and we'll take it to be a divisible ordered abelian group. And we'll see why in a moment. So what's the difference? How does a Hahn series sort of generalize a Puzzo series? So the series now, S, has the form, well, it's the sum of terms a to the g, t to the g, where these a to the g's, again, come from the coefficient field K. But now I'm going to require that they're non-zero here. And these exponents g come from a well-ordered subset S of this fixed group G. Right. And we're going to use as the collection of all of the Hahn series for K and G this notation. So double regular parentheses. Once again, I always need an example to look at to sort of see how these look a little bit different. So in this example here, I've got my concrete example S, and I'm going to take my exponents to be coming from the group of the rationals. So let's take pi t to the 0 plus t cubed plus minus t to the 3.1 plus 3t to the 3.14, et cetera, et cetera. So I'm starting in the exponents to approximate pi, and we'll keep doing that, just do the decimal approximation of the exponents. But then I'm going to add on to the to the end of this series, t to the 4th. Okay. So the support here, we can again talk about the support of a series will just look like this. So I'm just pulling out all those exponents, right, that start to approximate pi. And then, of course, at the end, I've got my 4. So if you're thinking about the order type of the support of this element, well, that has order type omega plus 1.
So any order type is reasonable?
Any order type you want would be a Hahn series. Exactly. So what are we interested in? Well, we're interested in the complexity of this root taking process. So specifically, let's imagine that you're handed a polynomial, p of x equals a0 plus a1x plus ... a to the n, x to the n, where all the ai are all Puzo series or Hahn series. And our goal is to describe the complexity of the roots of the polynomial in terms of the coefficients, the field k and g. And already, given what you're seeing about the supports of these elements, it's sort of probably natural to realize that, hey, the complexity of this problem very well might have to do with problems about well-ordered subsets of G. So we'll see that at the end. But let's start with root taking in Puzo series, all right, in the sort of simplest setting. So here again is what they look like, right? So these have their order type. They can only have sort of order type omega for their length. They're much more normal series in that sense. Okay. And one thing that's, oh dear, I did feel like my slide, I'm like, oh dear, maybe my slides, I've been missing something at the end this whole time. So let's see. So what's going to be incredibly useful for finding roots for Puzo series is that the Puzo series and Hahn series have a natural valuation associated with them, right? And I'll often call it the valuation, but it's W, and some people call it the weight of a series. And what the weight of a series is, well, by definition, it's just the minimum of the support of the series. So you're just taking, for example, in this series, the exponent of the minimum exponent is -1/2. So that's the valuation of this element. You want to think about the valuation as telling you what's the leading term here, which term has greatest weight in this series. And one thing that's helpful to keep in mind if you're trying to be like, oh, -1/2, why is that the greatest weight, weighted element? It can be useful to think about the indeterminate t as an infinitesimal, because then in that case, t to the q will get more infinitesimal if q is positive, and t to the q will be infinite if q is negative. So that's why you can sort of make sense of why -1/2, or this first term, 3t to the -1/2, is the leading term of this series. Okay. So I'm realizing that because I'd cut off my slides before, I didn't state the very important fact. So I'll go back a few slides and state this, that which Newton and Puzzo proved, is that if you're in the field of Puzo series over K, and your K is an algebraically closed field, well, then the field of Puzo series is algebraically closed as well. So of course that's important here because we're interested in finding roots, so we want to know that they exist. And we have the same fact for Hahn series, that if you've got K again algebraically closed and G is a divisible ordered abelian group, well then the Hahn field is algebraically closed as well. So I just want to go back to that because it makes, otherwise it can be hard to find roots if they don't exist. So that's why we took K and G as we did. So now let's return back to, well, how do you actually find these roots in the Puzo series setting? And here it's fun. This is where I really enjoy sometimes computable mathematics in the classical sense of like going back and thinking about an algorithm and thinking about what computationally goes into this. And so we're going to do that in this case. So we're going to study the classical Newton-Puzzo method over Puzo series. And so just, of course, to fix my notation, my polynomial P of x will always look like this. And let's assume that it's a non-constant polynomial, because if it was a constant polynomial, well, it only has roots if it's the constant 0 polynomial. And of course, A0 being 0, if the constant term is 0, well, that implies that 0 is a root of that polynomial. So we're really interested in the case where the constant term is also non-zero. So how does the Newton-Puzzo method work? Well, just big picture, we're going to construct this thing called a Newton polygon, okay, to approximate a root to this polynomial, right? So really what we're going to do is, rather than just trying to find the root, we're first trying to figure out, well, what's going to be the leading term of this root? And the leading term, we have to pick it carefully to make sure that we can cancel it off, right? We're just trying to plug something in and get 0. Okay. So I thought a good thing to do would be to actually do an example of building a Newton polygon, right? And show you how that works in a very made up friendly example. Right? So in my example, I'm going to take the polynomial to be this one. Okay, so here's my A0, here's my A1, here's my A2 and my A3. So it's a cubic polynomial. And I just cooked it up, by I wanted something that looked a little bit interesting, but the roots of this polynomial are just t itself and t to the 1/2 with multiplicity 2. So of course we don't actually need Newton's method when I cook up the polynomial, but it'll at least show you how do you actually go about computing these things. Right? And all of this, of course, is very, very old. All right. So I said we're going to draw some Newton polygon, which will help us organize, what should this leading term look like to make sure that this leading term will cancel off. So what the Newton polygon consists of points, I, comma, the weight of AI for each coefficient, right? And then we're going to just draw it to be a convex, connect the dots so that we get something convex. So let's do this for this particular example. Okay. So first, I'm plotting my points in blue. Okay, so 0, weight of A0. So the valuation of A0 is 2 because that's its exponent. So I'm plotting 0, 2 here. And then A1, well, I have to plot 1 and then the valuation of A1. Oh, it's not 3/2 though, it's t to the 1 because there's a hidden exponent 1 there. So I plot 1, 1. And then A2, I'm plotting 2, comma, the valuation of that leading term, which is 1/2, and so on. So that gets me my blue dots. All right. And then to make it convex, well, I'm just going to force it to be convex. So how I'm going to actually decide where to draw lines is I'm just going to drop a ray, straight down from this 0, 2 point. And then I'm just going to swing it around counterclockwise until I hit my first point. And so that's how I get that first side of my Newton polygon. All right. And of course, that's how I'm building it to be convex. And then I do the same thing from the second endpoint of that side. I drop down my ray and then I swing it around and I actually get this side, which has all 3 points on it. So if you notice, the slope, well, I calculate this. The slope of this first side is a -1. And the slope of this second side here is a -1/2. And you may be like, hey, wait a minute. The root, we know we have root t to the 1/2 with multiplicity 2. Well, that has an exponent of 1/2. And we also knew that this polynomial had a root t, which has an exponent of 1, which is hidden, of course. And these slopes are the negative of those valuations. So is that a surprise? And the answer is no. So that is what this construction is trying to organize for you. Okay, so specifically, we're trying to figure out what the valuation of our leading term is, what that nu is going to be, right, as we start approximating this root. And it will always be that the valuation, of at least one root, which starts with bt to the nu, will be the negative of the slope of a side. Okay, so that's basically, I mean, I'm not going to prove any of this, here, but that's basically the idea of this Newton polygon is that, hey, the leading term, the valuation of the leading term of your root will be the negative of your slope of one of these sides. Okay. Let me wave my hands though a little bit about why this is true, or at least give a heuristic proof of why this is true. So what are we trying to do here? We're really just trying to plug in you know, a leading term with, you know, our first approximation of this root. And we're just trying to plug it in and get 0, right? Well, when you do that, okay, what the idea of the Newton polygon is that the idea is that if 2 points, if you're looking at, you know, if you have a side of the Newton polygon and you have, you know, the 2 points on it corresponding to 2 coefficients or whatever coefficients, sorry, whatever indices up here. So for example, in this side, though the endpoints come from coefficient A0 and A1. Well, the idea of the information the Newton polygon is organizing is that it's telling you, hey, when you plug in this leading term, there's going to be a way to cancel off this leading term just involving coefficient A0 and coefficient A1. Okay, so that goes, and so let's see what's going on with that, or what's going on there. So imagine that, okay, I'm plugging in, you know, this first approximation to this root, and I'm getting 0. Well, in order for A0 and this A1 times bt to the new to actually cancel off and get 0, and for the other terms not to be involved in that cancellation, I would need that the valuation of A0 would cancel off the valuation of A1 times bt to the new. But since you know, yes, that's only the first term, bt to the new, but everything else is just going to be more, you know, have less weight to it, or it's not a leading term anymore. And so properties of valuation tell you that the valuation of this product is just the valuation of the individual pieces added together. So you get this equation that, okay, valuation of A0 is equal to valuation of A1 plus the valuation of that leading term. And well, that leading term, its valuation is just nu, because that's the exponent. So then you get this line that WA0 is equal to WA1 plus nu. And if you move that equation around, so you move this A0 to the right-hand side and you move the nu to the left-hand side, well, you're getting the slope of this side of, you know, the segment BC to be negative nu. Okay. So I know that's not exactly a proof, but hopefully it shows you why there's going to be a connection between the slopes of these sides and the valuation of, you know, the leading term in your first approximation of the root. Now, of course, that just tells you how to use your Newton polygon to actually compute valuations of terms, right? Basically, you're like, okay, I'm going to be using these slopes to tell me what the valuations, what the nus should be. But you also have to calculate. Oops. We also need to calculate. Oh, actually, I'll get back to that. The other thing I should say that's very useful here is that the convexity of this polygon tells you that the slopes are increasing. So that tells you that the root of greatest valuation will be associated with the leftmost side. And we see that actually in this example, right? That here's root t that has valuation 1, and you know, root t to the 1/2. Well, a half is less than 1. So where this convexity fact actually is going to prove useful to us later on. So I just wanted to point out. The other thing, of course, that we need to approximate is we need to actually figure out, hey, what's going to be, you know, we're interested in not just calculating nu, we need to figure out what that coefficient is in front of t to the nu. Well, to do that, once you've figured out how the weights are canceling out, then you just want to make sure that your coefficient b makes sure that the actual coefficients cancel out. So to calculate that b, that coefficient in front of t to the nu, well, you find the root of a polynomial over k determined by the leading coefficients of the terms on the corresponding side of the Newton polygon. So in this case, we only care about coefficients A0 and A1. We're just trying to make them cancel this leading term off. And the leading coefficient in front of A0 is a -1. So that's where I'm building my polynomial. I'm building a new polynomial to find a root of over k. And so that's where I get that -1. And then for this, then the leading coefficient on A1 is 1. And so that's going to say that, okay, to calculate the coefficient B, I've just got to find a root to this polynomial. Well, of course, that's a very easy polynomial to find a root of because this is a made-up example. But it has, it's a linear polynomial, has root 1, of course. So our leading term will be 1 t to the 1. So that 1 came from solving for the nu, right, and looking at the negative of the slope here. And then this 1 was finding the root of this polynomial over k. Right? Now, we actually know that t itself is a root to this polynomial because I cooked up this example. But in general, you wouldn't know that. This would just be your first leading term. So hopefully that gives you a little bit of flavor to how classical Newton's method works, or one version of Newton's method is this Newton polygon trick. Okay. And of course, then you're going to have to repeat this process, right? In general, we have now found, the leading term, the first approximation of this root. But now you'd have to figure out what the next term is in this root. Well, to do that, you do the natural thing and you consider, the polynomial p shifted around this leading term, bt of nu. That'll give you a new polynomial. But if that new polynomial has constant term 0, well, then that tells you that, hey, just that leading term by itself is a root. And if it's not 0, well, then you can just repeat this process and continue to approximate as you need to. Okay. So now that we know the classical approach, let's talk about how to actually, really couch this in computability theory. So first I have to say, how am I going to represent Puzzot series in this setting? As usual, let's assume our K, our field K has universe omega. And let's fix a computable copy of the rationals, right? Again, with universe omega, just as usual, do the usual coding. Well, now, if I have a Puzzot series S, just as I did before, it has the same form that I described before. I'm going to represent S by a function from omega to k cross q, so that f of n, if f of n is the pair an q to the n for all n, well then S is just going to be the sum of the terms an t to the qn. With a few caveats, I'm going to want that my qn increases with n, right? So that's sort of it's an actual approximation of my Puzzot series. And also, this is a Puzzot series, so there is going to be some uniform bound on the denominators of the qn terms. And that just comes from the definition of Puzzot series. So the comment I want to make is, we're assuming the qn increases with n, but because there's a bound on the denominators, well, these qn's, the limit as n goes to infinity of qn will be infinity. Right? And that'll be a useful fact for us in just a bit. So I think it's a very natural way to encode Puzzot series. It sort of looks like a series definition. So then, before we can talk about the complexity of root taking itself, we have to talk about the complexity of just the basic operations between Puzzot series. Well, the good news is, given two Puzzot series represented as described, you can effectively compute their sum and their product. Right. But it's not surprising. You could probably even, just from the definition, it's only pi. It's pi1, but it's not computable to say that a Hahn series is 0. And so that's sort of the sad usual thing of, well, it's looking like it's 0 so far, as I've described the series, but, maybe later on I'll see that it has a non-zero term. Right. So that's too bad, but that's life. Okay. However, given that you know S is non-zero, then you can effectively find its valuation, right? Because once you know it's non-zero, well, you just have to list out terms until you see the very first term, and that'll actually give you the value. That first term will actually give you the valuation. Regardless, though, of whether S is non-zero or not, we can effectively order the valuation of S, or compare the valuation of S with any rational number. Right? That's because we're giving our representation, we're describing, the QNs are increasing. And so, well, we can compare the valuation of S to any Q, to any rational number, just by saying, well, do we see a non-zero term before this rational number or not? Okay. So even though it's not computable to say if something's zero, we have a lot of ability to approximate things here. All right. So what's the result that you can get? Well, you can get that there is a uniform effective procedure that, given K and the sequence of coefficients for a non-constant polynomial over Hahn series, that yields a root. Okay. So what the issue here, of course, why are these for non-constant polynomials? Well, it's because we can't tell whether a polynomial in a uniform way, whether it's non-constant or not, right? Because we can't tell whether any given coefficient is zero. So as a corollary to this, we can't say that in general you can uniformly compute roots, but we can say that given any polynomial over Puzzo series, all roots are going to be computable in K and the coefficients of that polynomial. So I want to say just a bit about how you get this theorem, this uniform result. And we've already sort of, highlighted kind of what the issues are here. As we saw, the big sad issue is that we can't effectively determine if a coefficient AI is equal to zero. So remember, when we were doing Newton's method, we wanted to check, for example, that the constant term would be zero or not, right? We wanted to be able to say, hey, is zero just a root of this thing, or do I have to do some more work? So we can't do that effectively. The other thing that we can't do effectively is actually compute the valuations of coefficients and related terms as we go. So it means we can't uniformly compute the Newton polygon. Okay. But what we can do in terms of valuations is we can approximate them to whatever precision that we want. So rather than uniformly computing the Newton polygon, what we can do is we can approximate pretty closely, or as close as we want, what the slopes of the Newton polygon are and things like that. Okay. The last issue is related to the first. We can't tell if the root R is a finite sum, right? That has to do with, at some point we might be done, but we can't tell that we're done because we can't tell whether A0 is equal to zero or not. So this is usually, so the issue is we might be done, but we don't know that we're done. Well, we think we're done, but we're not actually done is really the issue. So it's a situation where we're needing to append terms to our Puzzo series, but we also need to allow the possibility and append correct terms or good enough, be careful in how we're appending terms so that if we need to continue adding more terms later, because we found out some coefficient was non-zero, we still have enough space to do that. So essentially this theorem becomes, the procedure really becomes being very careful in how you're approximating and making sure that you've approximated with enough precision so that you can add terms without messing up your chance to start adding more terms later. So it's that kind of typical game. So let's turn now to talking about Hahn fields. Okay. So everything's nice in some sense, right? We can say that in Puzzo series, this is totally computable, which probably Newton and Puzzo was like, of course it's computable. Look, here's an algorithmic way to approach. So just to remind you about the difference between Hahn series and Puzzo series, the difference is here, our lengths can be arbitrary order type. Okay, right. As long as your support, your exponents are a well-ordered subset of G, you're a perfectly good Hahn series. And we, just as before with Puzo series, we have a natural valuation, which is again just the minimum of the support. So in this example, the valuation of this S is just 0. Okay. As I mentioned earlier, the length of this this series is omega plus 1. So this one's not even a very long Hahn series. Well, as I said earlier, we know classically that that Hahn fields are algebraically closed as long as K is algebraically closed and G is an ordered divisible group. Okay. So what goes on in this setting in terms of computability? The first thing that we have to do is decide how are we going to represent Hahn series. And I'm going to show you two approaches, and I'm going to use one in one context and another in another. But they're both sort of natural in their own right. So the first way of representing a Hahn series would be to generalize what we did with Puzo series. Just be like, okay, well, we know that they have some ordinal length, so let's take a function f. So say here's your Hahn series. Well, then let's represent it by a function which goes from an ordinal alpha to k cross g, such that if f gamma is equal to a gamma g gamma, well, then the Hahn series is just the sum of the terms a gamma t to the g gamma, where these g gammas are increasing in terms of, they're increasing in terms of their index. So this is just purely generalizing what we did, the representation that we used for for Puzo series. One sort of downside about this approach is that, like you're sort of hard coding information about the length in. Before with Puzo series, there was only 2 lengths. Well, it was sort of finite or infinite, right? But now there's sort of all whole new kinds of lengths that can be involved here. So another approach that you could take to represent a Hahn series would be to just think of it as a function going from G to K, where this function sigma that represents S, well, it's non-zero precisely on the support of S. Okay, so and then what is it? Well, it's just going to give you the coefficient that goes in front of, that sigma of G is the coefficient in front of the indeterminate t to the G. So this function's just encoding, hey, on an exponent G, what should be my coefficient in front of me? So we're going to start by using this first approach, all right, to think about how to represent Hahn series. And there, if we take this approach, we can show that, well, we can't show that you can take roots in a Hahn field, computably, but we can get an upper bound of that you can carry out this process in an admissible set. So an admissible set, right, it's just a model of set theory, right? It's a transitive set that essentially satisfies the axioms of ZF, but no Powers axiom, and the axioms of comprehension and replacement restricted to delta 0, formulas. And then a few other kinds of formulas. So of course, the point of working in admissible set is that it's a generalized setting of computability. So, if you're looking like you're dealing with a process which isn't necessarily fully computable, well, maybe it can be carried out in an admissible set. And so of course, the key example to think about with admissible sets is L omega 1 CK, which is the least admissible set containing omega. And the subsets of omega in that example are exactly the hyperarithmetical sets. So that's why it's a natural place to move to if you're thinking you're dealing with something not a process not fully computable. And the good news is, or why I chose to look here, is that we can show that you can carry that the generalized NewtonPuzzo theorem holds in any given admissible set containing the field K and the group G. So what do I mean specifically by that? I mean that, hey, if you've got a polynomial with coefficients from the Hahn field KG, such that this whose coefficients are in the admissible set, well, then that polynomial will have a root that is in the admissible set. So why can we carry out Newton's method for Hahn fields in this setting? The first key is that when you're working in admissible set, you can define functions by induction on the ordinals, as long as you have a sigma 1 formula describing how to obtain f of alpha from the previous images of f. Okay. What else do you need, though, in addition to that sort of standard, like what's great about working on in admissible set? Well, other tools that you need is you need to have you need bounds on how long roots can be. So as Peter mentioned before, you have to, he's like, can Hahn series be arbitrary order type length? They can be. But what Julie and I have showed in some earlier work is that if you have a polynomial over a Hahn field and you have a gamma, a limit ordinal, greater than the lengths of all AI, of all the coefficients AI, well, then any root of P of X has length less than omega to the gamma. So this is saying that as long as your coefficients don't have too long of lengths, well, then your roots can't have too long of lengths. They can get bigger, but they can't get that much bigger. So again, going back to why we can carry out the generalized NewtonPuzzo theorem in this setting, well, as long as you're working in an admissible set, well, the function going from, say, for example, alpha to omega to the alpha is sigma 1 definable. So that's going to mean that, hey, if you have, if you've got a gamma, an ordinal bounding the AIs, well, in an admissible set, you're also going to be able to get omega to gamma in that admissible set. Also, good news is that as long as you're in an admissible set and you have two Hahn series S and S prime, well, then their sum, their product, their supports, and their lengths are all going to be in that admissible set. So you can actually work with, you can work with these series very, very easily and do sort of your basic computations. So those are the tools that go into showing that you can take roots in a Hahn field, right? But that gives you sort of a large upper bound. Okay, you can do this in any admissible set if you want to. But we wanted sort of finer grained information about how hard is it to actually go about computing these roots. And so what we then looked at was thinking, okay, let's try and figure out the complexity of how hard is it to get initial segments of roots, which is actually sort of what we naturally do, like what we did with Newton's method with Puzzo series, is like we actually approximate what these roots are up to some length. So we wanted to say the complexity of that procedure. So as usual, we've got our polynomial, P of X. And then we wanted to say, okay, well, how hard, is it to, so at step 0, we have our first approximation of our root, well, it'll just be 0, right? But then we want to have at a later step alpha, we want to have an approximation R alpha, which has length alpha and extends all of the approximations that we've had so far, or at step alpha that we've already found a root to our polynomial at some earlier stage. Right? And so then if in that case, we'll just set R alpha to keep outputting, at our new step, we'll just keep outputting the same root. So the idea here is we just at step alpha, we want to know an initial segment of R alpha, a root of P of X. So we're not asking for the full root, we're just looking for that initial segment by step alpha. And so here what we're going to do is we're going to view R alpha as a function from G to K with well-ordered support. So we're going to take that second approach to encoding encoding Hahn series, in the sense that now our alphas, our approximations, are non-zero on group elements that appear as exponents, and they output what coefficient goes in front of that t to the g term. So then, to get sort of a finer view of how complicated this procedure is, well, let's bound the complexity of carrying out this procedure to step alpha when given k, g, and p. Well, I can tell you an upper bound, okay? Sort of if you just do it, if you're just trying to carry out the procedure, here is an upper bound, what you're seeing. But it's easier just to write out what these bounds are for the first few levels. So step n, up through step n for finite n is delta 2. At step omega, it's delta 3 to find these initial segments. Step omega plus n, it's delta 4, and omega plus omega is delta 5. And really what we're seeing here is, in all these examples, tells you how this function grows in general. Basically, at limit stages, you go up, you go up a level, and then after a limit stage, then you go up one more, and then repeat. Okay. We also know that these first three lines here, step n through step omega plus n, those are sharp. But at step omega plus omega, we don't know whether we have a sharp upper bound or not. And I should say, this is sort of you're not working very hard to get these upper bounds. It's just sort of like, oh, what needs to, just what kind of power do you need to have? So we don't know that these upper bounds are sharp, but we do know that complexity does go up with ordinal length, right? That as alpha goes up, step omega to the alpha is pi 2 alpha hard. Well, how do you get this? I'll just say a little bit about this. Well, the key ingredient to showing that step omega to the alpha is pi 2 alpha hard. Well, you're going to use this old result that, given a pi 2 alpha set, there's a uniformly computable sequence of orderings, Cn, which are subsets of the rationals, which has order type such that Cn has order type omega to the alpha if n is in that pi 2 alpha set, and has lower order type otherwise. And so then you can let's take Bn to just be the Hahn series, which is just the sum of t to the q's, where q is in C of the n. So then if you look at the polynomial Pn, which is just the linear polynomial Bn minus x, well, that has a unique root Bn, of course, right? And if n is in S, well, then you actually needed to carry out this procedure through step omega to the alpha, right? Then you actually had to keep figuring out more and more of what the initial segment looked like. But if n isn't in S, well, then you didn't have to actually, then at that step, you're not doing anything new. You're just outputting a root that an earlier initial segment. So it's a way of viewing that this pi 2 alpha set is reducible to what's going on in this procedure at step omega to the alpha. The only thing that's very disturbing, or not disturbing, but that's a little bit like about this kind of hardness result, is all we're using here to get it is a linear polynomial, right? We're not using the field multiplication in any way, right? We're not using a quadratic or something like that. Really, this is just happening. You're not using the multiplication in the field in any real way. And so this result, it seems like maybe there's either room to bring these upper bounds down, right? Like if we're, like that would be one possibility, or that may be the reason why we haven't been able to show like step omega plus omega is sharp yet, is because we're really not using the field multiplication. And so well, if we're going to get better bounds on this view of the root-taking process, one thing to do would be like try to take advantage of the multiplication in the field in some way. So notice that if I've got a Hahn series S, well, the support of S squared, well, that's, the support of S squared is just what exponents show up in S squared. Well, that's going to be the sum of pairs of elements in the support of S. And that support is also well ordered. So to try and better understand what's going on with the multiplication, or how to leverage the multiplication to maybe, get better lower bounds on this process, it's natural to consider the complexity of problems associated with well-ordered subsets of G. Right, sort of just look at, well, what can we code into these exponents basically in the Hahn field? So the kinds of questions or problems that Chris Hall and Julia are studying right now are problems associated with well-ordered subsets A and B of G. So for example, how hard is it to check that A has order type at least alpha? And then a related question, well, find the alphth element of A. Okay, so we know how hard those, we know how hard those things are. But then, since we're trying to think about the multiplication of the field, that really has to do with adding two subsets together, right? Taking the set of sums of an element first from A and added to an element in B and B. Well, how hard is it to check that new set, A plus B, has order type at least alpha? And how hard is it to compute initial segments of A plus B? So it turns out, I'm not going to say a lot about these results. Basically, these two first problems have the same complexity to each other. That doesn't help you add yet additional complexity than what we saw in that hardness example where we were just using linear polynomials, or in that hardness proof. But what looks more promising, but we haven't figured it out yet, is if you have a subset A of G, which consists of non-negative elements, well, then the set of finite sums of elements of A is well ordered. So that's just true. And checking to figure out whether the order type of that collection of finite sums is at least alpha, that seems like it has the potential to require more computational power. So we're still working on figuring out what's going on here, and some related questions. So just to wrap up, let's just review what we saw together. So we saw that Newton's method, classical Newton's method over Puzzo series, is uniformly computable in K and a non-constant polynomial. So that's kind of very nice, right? Newton would view this as a computable, viewed it as probably computable originally, and it really is. And we saw that Newton's method for Hahn series can be carried out in any admissible set containing the field and the group and any polynomial in question. And then lastly, we're seeing that this latter problem naturally involves the complexity of problems involving well-ordered subsets of G. And so I do hope that I'll have more to say about that for you in the future. Thanks.
Thank you, Karen. We could all clap or give her a thumbs up or whatever you want to do. So questions, unmute yourself if you have one.
So for the theorems that you just mentioned, you don't need to know what's the degree of the polynomial is, you just need to know that it's 2 or higher, and then it will work.
Yes. So, yeah, no, it is interesting. The degree does not. I mean, do you mean the like these upper bounds?
Just for the, that you had the more or less uniform algorithm for the Pozzo series.
Yes. So it doesn't. The degree does not come into play. That at all. I mean, it's basically it's yeah. No, that's actually, it is sort of surprising that for all of these things, the degree doesn't. Well, I should say I don't really know what goes on. We don't fully know what's going on in the Han series case, but certainly in the Pozzo series case, the degree does not matter. Yeah.
Would you dare to speculate over like what abstract properties of that field from a computational perspective, in a sense, makes that work?
About why the degree doesn't matter. I like how you put it, dare to speculate. I'll vaguely say, like, I mean, it's really because this construction of, it's really that Newton's method is about figuring out which coefficients cancel with each other. And the degree, it's sort of that the complexity doesn't come with degree. I guess with Pozzo series and actually all of these, I mean, just this Newton polygon that we're drawing, that's really just about the coefficients involved. Let me see if I can pull up this picture again. So I'm vaguely and probably incoherently speculating here. Wait a minute, why isn't it loading? Okay, so when you're drawing these Newton polygons, it really doesn't matter. I mean, you're just interested, the degree turns into these, like the degree gets taken into account in these slopes, but it doesn't, yeah, I mean, it really doesn't add to the, it makes it so that the difference between dealing with a cancellation happening between A0 and A1 has no sort of more information that you're trying to get canceled off than what's going on between coefficient A1, A2, and A3. Maybe it's in some part to do with that when you take degree here, when you're looking in valuation terms, degree just has to do with this exponent. But when you look at exponents under valuation, they just turn into sums. And so what would happen if I was looking at the A2 term is I would just get, like if I just squared that t to the, if I was looking at b, like r squared, the valuation would just end up being that would turn into 2 nu. So that's not, I know that's a very not exactly clear reason, but it's sort of that you're paying attention to the exponents and everything becomes additive. Yeah. So I would strongly recommend, like, if you're interested in that issue, really spending, like, I found really looking at these Newton polygons very satisfying. So that would be a place to go and sort of see why degree doesn't matter so much in calculating these first terms. Maybe that's a good answer. It's because you're really just approximating rather than, it's that view of approximation that it seems like impacts why it doesn't matter what the degree is.
Also, the number of steps it takes to finish is probably going to be omega, no matter what the degree of the polynomial. And all you're doing is replacing one degree 5 polynomial by another degree 5 polynomial when you go from one term to the next. You're not really...
So all the solution
with the polynomial when you pass from one term to the next, but you get done after omega many steps anyway.
That's maybe another way of saying it. Yeah, that sort of, you're no worse. I mean, that the worst you can take is omega many steps anyway. Although that's more about steps than computational complexity, I guess. But yeah, what were you going to say, Peter?
Well, so the whatever you call it, the ordinal that's involved. for the solutions, it could be very complicated, right?
For Hahn series, but what Julie is pointing out in Puzo series, at worst, it's omega many
Omega.
steps. Yeah,
Yeah,
so
okay.
yeah.
Other questions?